So Henry is currently working as a postdoc research associate at the University of Edinburgh, and he used to be a PhD student of Bernhard at the University of Waikato. So that's how I got to know Henry, and I actually only met Henry in person twice, and both are at conferences before COVID. And I've always been very impressed by Henry's theoretical understanding of statistical learning. So he's my go-to guy if I have any question about the theoretical stuff. And recently we had a couple of people at the lab reading Henry's paper on regularizing neural networks by forcing Lipschitz continuity. So I thought we should invite Henry to give a talk on some of his recent work. So thanks, Henry, for agreeing to give a talk, and welcome.
Thanks for the introduction. So before I get started, I guess I should check that I've actually managed to share something.
Yeah.
So I guess you can see some not quite maximized.
Yeah,
okay.
Oh, can you change the view? Yeah, cool.
So is that working?
Yeah.
Excellent. Okay. So as I was just saying, as people were still joining, there's like I asked Alex to send me like a list of like a link to a web page with like a list of people who I might be giving a talk to, so I could try and pick something that would be relevant. And it turns out, as with most places, there's quite a diversity in topics that people are working on. So I've just sort of jammed a few vaguely related things together to construct this talk. And the underlying theme is using ideas from statistical learning theory to provide either sort of post hoc justifications for existing methods, or to possibly use as inspiration sort of underpinning ideas for future developments for certain types of problems. So I'll get started with what I'm talking about today, which is using statistical learning theory to analyze generalization in two particular problem settings. So one is domain generalization. So that's generalizing to sort of out of distribution data that your model might not have been trained on, and also meta-learning, where you want to automatically construct a learning algorithm that can then learn very sort of sample efficiently on new tasks that you haven't seen. So the rough overview is I'll give you like a bit of an introduction to Rademacher Complexity, which is my sort of preferred theoretical tool. Now, just sort of a little bit of disclaimers that I'm not going to go through like the real derivation of Rademacher Complexity. I'm going through something that's more of an interpretation that I think people who are more familiar with like sort of applied or empirical machine learning research will be able to understand a bit better than just having lots of equations thrown at them. So I've tried to keep things sort of to like things like word equations and diagrams, but with a little bit of like sort of actual equations popping in there just to tie things together a bit. And then I'll show you how you can adapt some of these Rademacher complexity bounds to domain generalization and meta-learning, and then summarize with a little bit of outlook about where I see the things that I'm talking about today going in general. So, so one way you can sort of think about the standard sort of way that we apply machine learning to problems is that you begin by picking some idea of a hypothesis class. So in general, so Rademacher complexity is extremely sort of general. It's not specifically for, say, neural networks or specifically for linear models. It's you sort of use these bounds or these theoretical tools for all sorts of machine learning algorithms. So you begin by, in general machine learning sort of practice, you begin by hopefully or possibly explicitly defining some sort of hypothesis class. So for an example, this could be, you could pick a neural network architecture, like your favorite architecture, like ResNet 50 or something like that. And then your hypothesis class might be, for example, all of the possible weight vectors that you could load up into a ResNet 50 in PyTorch. So it's all of the possible sort of like, state dictionaries for a ResNet 50. And then you gather some training data set. In this case, I've used the sort of standard example that's nice to look at in slides of cats versus dogs. And then you pump both of these things into some optimization algorithm, which I've represented by PyTorch. Again, it's actually much more general than this. You can use, if you're doing stuff with decision trees, maybe you're using J48 or C4.5 or something like that. And then out from that optimization algorithm picks one particular configuration of weights that was inside your hypothesis class. Then you can apply this learned model to some new data that you haven't seen yet. And then you can get, you can use that in sort of a research context, at least, to figure out sort of, some interesting question, some sort of quantifiable question, like, how badly have I overfit, which in this case is represented by the generalization gap, which is the difference between your test set error on these new images and your training set error on the images that you use for training. So hopefully all of these ideas are relatively familiar. This is like the sort of standard pipeline of things that they teach you in sort of introductory machine learning things. This is how you train a model without being too overconfident about how well you train the model. Maybe the idea of having a strictly defined hypothesis class is slightly out there in terms of neural network land. But for things like SVMs, that's sort of a relatively well-defined thing to do. So this whole sort of pipeline of generating an estimate of how well you've either overfit or sort of fit or generalized to new data is called holdout evaluation. You can also take this one step further and do something maybe slightly more reliable and do repeated holdout evaluation. So again, I assume that a lot of people will be kind of familiar with this idea, but this is a useful way to set up Rademacher complexity and how you can interpret it. So again, with repeated holdout evaluation, you take your training data, you pump it through some optimizer. I've assumed, sort of, to keep this slide a little bit less visually noisy, I haven't included the hypothesis class part of the diagram, but just pretend it's still there. You pick a particular model using your optimizer, and then you train it, you evaluate on some test set. And then for repeated holdout evaluation, you use a different train test split, but the same underlying data. And you might get a different estimate for your test performance. And then for the purposes of this particular talk, we'll assume that the training and testing folds don't necessarily have to be the same size for every iteration. So everything's sort of, probabilistic. You have maybe equal chance of assigning each individual instance to the train versus test set. Anyway, once you've done this several times or many times, then you can take the mean of whatever you're trying to estimate, whether it's the test error or this generalization gap, and that this is hopefully a more reliable estimate than just doing this holdout evaluation process once. Now, this is where we start to deviate a little bit towards the statistical learning theory side of things. So what I'm actually going to be talking about, or what statistical learning theory generally assumes, just to sort of allow itself to be a little bit more separated from what people do in practice, which is sometimes a good thing, sometimes a bad thing, is that they assume that you're using the optimizer that will overfit the most. So this is some hypothetical optimizer. It's not necessarily something you can actually implement because, for example, in the context of neural networks, everything's like this big, messy, non-convex optimization problem. So this hypothetical or abstract worst-case optimizer is, finding the globally worst solution in your hypothesis class. It's not just doing some sort of local optimization. So now we get on to the case where we have this generalization gap. So we can define this generalization gap a little bit more concrete. So I've expanded the definition a bit just to make it a little bit clear about how everything fits together. So we've got this supremum of F in our hypothesis class, which I've said is like sort of, the globally worst optimizer, or the worst optimizer that will find, well, the optimizer that will find the essentially not the worst model, but the model that will overfit the most. So it's the one that will have the biggest difference between your test error and your training error. So you can see that all I've done here really is make the choice of optimize explicit compared to when I had the definition of generalization gap earlier, and also expanded the definition of your training error and your test error for this small data set that we've got. So the first three terms are just the test error, and then the last three terms, there's subtractions happening there instead of additions, your training error. So this is just computing the difference between your test and your training error. So it's just the generalization gap. So what we can do if we want is change everything into just a sum. So we get rid of those minus signs, change them into plus signs, but then we introduce some sigma variable in front of each term so we can control the sign of that term. So if we set sigma to 1 in front of each term, then in front of some of the terms, then that's assigning those terms to the test set, or it's assigning the corresponding images in those terms to the test set. And if we set it to -1, that's assigning it to the training set. So we're still getting this generalization gap, essentially. And so to start sort of introducing some real notation rather than using sort of picture equations, this is what we're actually computing. So we've now got a summation over all of our data, and we're using the sigma random, this sigma variable to assign each instance to either the training set or the testing set. And then we're looking at the model in our hypothesis class that sort of has the biggest generalization gap. Now, what we can also do is make sigma a random variable. So that's, I sort of alluded to this earlier a bit and said, what if we have equal chance, sort of 50-50 chance of assigning each image to either the training set or the testing set? That's exactly what this sort of probability distribution that we've just defined over sigma does. And then if we average over all of the different assignments to all of the different sigmas, then we get this. For those of you who have looked into statistical learning theory before, in particular Rademacher complexity, this should hopefully be kind of familiar. So this is actually just the definition of Rademacher complexity. So again, I've skipped over a few details and sort of like fudged a little bit to sort of help convey intuition. So this is not like the super rigorous way that people actually derive Rademacher complexity in practice. I've sort of tried to use empirical analogs to some sort of abstract theoretical quantities to help make it a bit more clear about what's happening. But this is providing the right intuition for what Rademacher complexity actually means. So I think there's sort of, when people try to learn about Rademacher complexity, one of the things that one of the attempts at intuitive explanations that some people try to provide is that it's a measure of how well your model can sort of correlate with random noise, which I think is one of the least intuitive ways of describing it. And when they say random noise, they're talking about these sigma random variables that have equal chance of being positive or -1. I much prefer trying to sort of introduce people to Rademacher complexity using this idea of that, it's just sort of like a compact way of writing down the worst case generalization gap, the worst case difference between your testing and training error. So now, why do we care about Rademacher complexity? It's because it lets us derive this bound here. So you'll notice that a 2 has appeared. That appears if you actually go through the derivation rigorously and properly. Essentially, it arises because you're splitting your training set in half to construct your train and test folds for doing this repeated holdout evaluation. So this 2 sort of counteracts that splitting in half and the sort of rigorous definition or derivation. But something that's it still sort of amazes me sometimes that we can actually get guarantees on our test error just by looking at our training error and the sort of particular space of models that we're actually searching through to find the model that we're actually going to use. So this is a way of, at least in theory, of certifying the performance of a classifier without having any sort of test set or validation set. So there's some situations where that can be quite useful. I won't get too much into that, but it's just sort of like quite impressive to me, at least, that this is even possible to do in the first place. But what I tend to use this sort of analysis for more often, just to give you some more context, is more to find what sorts of terms Rademacher complexity ends up depending on, and using that for regularization purposes. So I'll go sort of a little bit towards that direction now, just with some examples about what you now do with Rademacher complexity. So typically, the next step after you've defined this Rademacher complexity object is actually to try and bound it for a particular choice of hypothesis class. And the typical bounds for bounds on Rademacher complexity look something like this, where you've got some notion of model capacity, which varies depending on what hypothesis class you choose. And then typically in the denominator, you have the square root of m, where m is the number of training examples that you had. So just a couple of examples. So if f is some sort of finite hypothesis class, for example, if you've defined some sort of like relatively constrained family of decision trees, then it might be the case that your hypothesis class is finite. So for example, the weak learners in XGBoost, if you're using like the histogram splitting functions, or the histogram splits, and the histogram representation for your features, and you're constraining the depth, then this would apply. So you end up with model capacity being less than or equal to, or model capacity being roughly the natural logarithm of the size of your hypothesis class. So that's the actual sort of number of elements inside that set. So the logarithm actually means that it doesn't grow that fast. So that's actually not as big a quantity as you might expect just looking at the cardinality of that set. That logarithm actually restrains things a bit. So for linear models, this is maybe a slightly more relatable example for people who deal with neural networks primarily. If you have a linear model where you've got some sort of upper bound on the maximum allowable norm of your weight vector, so this is just a binary classifier. So for example, this is the standard example you see if you're dealing with SVMs. Then you end up with model capacity is less than this sort of thing here, where it's the maximum norm of your input x times the maximum norm of the weight vector. So in practice, the maximum norm of x can be almost like a user-defined thing, because if you want, you can just normalize all of your features, like with L2 normalization or something, and sort of get rid of that term entirely if you feel like it. Just make it 1. Now, just to set your expectations, and I think this is something that Alex already knows and has possibly discussed with people, or maybe there's lots of people working on the same sort of stuff as Alex. The neural network bounds are really loose, and they're not actually that useful in practice in terms of actually explaining why neural networks work. So I just want to temper some expectations there a little bit. I haven't solved that problem. But I will talk a bit about how you can generalize Rademacher complexity from this standard sort of i.i.d. learning situation into some slightly more exotic learning situations, or learning scenarios. So the first one is domain generalization. So I'm not sure how widely known domain generalization is in this group, so I thought I'd just give like sort of a one-slide introduction to what the problem setting is. So it's a specific instantiation of dealing with domain shift, and it's this idea that you have, say, a few domains that you can, a few sort of distinct subsets of your training data that come from different domains. For example, I've got 2 face data sets here, or they're 2 separate face data sets, but you can sort of think of them collectively as one big data set. But half the data set has come from, I think it was a Japanese face data set, and the other half has come from like some, I think it was like a Hollywood or celebrities data set. So not necessarily Hollywood, but some celebrities. And the demographics of these 2 groups tend to be quite different. And then say, for example, you actually want to train a model on these data sets, but when you deploy it, you're going to deploy it where there's a lot of, say, African-American people. So I'm not going down the sort of like fairness side of this. This is just an example of a domain shift. But another example is if you're doing some sort of art analysis, then maybe you've got some paintings from Europe in one subset, some paintings from China in another subset, and then some African sculpture in another subset. And then maybe you want to generalize to a more sort of New Zealand context, where you have an entirely different sort of style of art happening. And then also in sort of medical image analysis, maybe you've got medical images that look a bit like this, and then you get one that looks a bit like that, which is maybe got sort of different calibration parameters, or the MRI machine, for example, is set up differently, so it produces things with different noise patterns or different intensities or different scales even. Those are all sorts of things that sometimes humans don't even notice when we're looking at these images, but it can break a machine learning model completely. And a lot of work in the medical imaging community or the medical image analysis community, like machine learning for healthcare sort of stuff, it's trying to deal with these sorts of issues. And also, that's just sort of like looking at the imaging technology. You can also get problems where, your training data set was gathered from, 2 different hospitals in the same city in North America, and you want to deploy this model in, say, New Zealand, where there's sort of wildly different population demographics. So, and different demographics tend to have different healthcare needs as well, and various other issues pop up. So there's all sorts of domain shift that can happen in sort of the medical imaging context as well. So domain generalization is this idea of training on some domains and being able to still perform well on novel domains that have some relation to the original domain. And the sort of big issue is that with both evaluation and also training a model that's going to work reliably, is that your training and testing sets are no longer i.i.d. And this is also what sort of prevents the application of existing Rademacher complexity and related sort of theoretical tools to this domain generalization problem. But the way that there's actually a relatively simple way to get around this, which is why I think it's sort of like a pretty good way of demonstrating my point that we can generalize learning theory to beyond just the standard i.i.d. learning setting. We can actually just move this i.i.d. assumption somewhere more convenient, or at least more justifiable. So it's sort of clear that on this slide, we're definitely violating this i.i.d. assumption. There's an obvious shift between our training sets and test sets. But maybe we can move this i.i.d. assumption somewhere where it's more justifiable or more likely to be true, at least in some domain shift settings, maybe not all of them. So instead, you can come up with a sort of like hierarchical data generation model where you've got some sort of high-level distribution, this calligraphic P, that then sort of generates latent variables or generates several different probability distributions of different, and each one of those probability distributions is associated with a different domain. So maybe that P1 is to do with the Japanese faces, maybe P2 is to do with the celebrity faces that was sort of centered on Europe and North America. And maybe there's a few more domains from, like, say, Africa or whatever that are entirely different again. So the assumption that we can now make, which is a little bit more defensible, is that our domains are selected i.i.d. rather than the data within the data in general are selected i.i.d. from the same distribution. So we've now got this sort of like stratification or this like sort of separation of all of our data points into different domains, and each one of those domains is now i.i.d. So we can now go through and define like the sort of same idea as in the standard i.i.d. learning setting. We can define some sort of domain generalization gap, so this DG gap. And that's going to be the difference between our test error, which I've denoted as test error OOD for out of domain or out of distribution, and train error, which I've got in domain in the subscript there just to remind people. And you can actually decompose this into sort of 2 different bits. So what I've done here, I'm not sure if you can see my mouse cursor, hopefully you can. These 2 middle terms are actually just the same thing. So I've just subtracted in-domain test error and then added in-domain test error again. And that's going to allow us to split things up a bit. Because what we said in this sort of first introductory section with Rademacher complexity is that this test error this in-domain test error and this in-domain training error are bounded by 2 times the Rademacher complexity of whatever hypothesis class we're using. So remember, hypothesis class is, our neural network architecture coupled with the sort of weights that we're going to allow it to have. So what we actually care about doing to generalize this Rademacher complexity sort of idea to this domain generalization setting is figuring out how to bound this thing here, which is what I'll go over in the next couple of slides. So we can go through the same sort of heuristic derivation process again to sort of gain intuition for how we can do this. So if you think, so this is a little bit of a summary of one of the standard sort of toy data sets that people in the DG community use. It's called PACS. And there's 4 different domains, and there's some number of classes that I've forgotten. But importantly, like, you have the same classes in each domain. So it's really just the modality that's changing, not the actual classes. So for example, one particular split, your test error might just be photos. It might just be measured on all of the photos. And then your training error is the sum of losses on the sketches, the cartoons, and the paintings. But again, this is just one particular way that we can split up this PACS data set on like sort of the domain boundaries, rather than just ignoring all of the domain annotations that each image has and just sort of doing some random allocation of some images to a test set and some images to a training set. If we instead sort of take into account these domain annotations that things have, we can split things up this way. And then we can do this. So I've left out a couple of sets this time, but hopefully the Rademacher complexity slide wasn't too long ago that you can't remember the rough idea about how it works. We can do the same thing where we define these sigma random variables to allocate different domains to the training set and the testing set, and then we can use again our sort of hypothetical abstract worst possible optimizer to pick the model that's going to overfit the most, and then we can average over all of the different allocations of domains between training set and testing set, and we get this sort of similar Rademacher complexity thing again. This time we've used n domains. So what we end up getting once we put this extra Rademacher complexity term together with that decomposition that was on the previous slide is that we get our out-of-domain test error is less than our in-domain training error plus these 2 different Rademacher complexity terms. So that Rn, the first Rademacher complexity term, is looking at how much did our model overfit to the particular domains that it saw during the training process. And the second Rademacher complexity term is looking at how much the model could have overfit the particular instances that it saw during the training process. So you get one Rademacher complexity term for each layer in this data generation process hierarchy. So there's a few sort of potential implications that this analysis has. So the first one, since this generalization bound for DG has 2 different Rademacher complexity terms instead of 1, which is what you find in the conventional learning setting. Does this imply that, and since Rademacher complexity is sort of a measure of model capacity, and we use regularization to sort of constrain model capacity in machine learning, does this additional Rademacher complexity term imply that we need stronger regularization in order to avoid overfitting as much? It turns out the answer is yes. So this blue line is is the test error of a model. So actually, I'll back up a bit. So this plot is a plot of performance of linear models trained on MNIST, but where we've sort of artificially constructed different domains in MNIST by rotating the digits by different amounts, or by rotating subsets of the entire MNIST dataset by different amounts. So some digits will be, or some instances will be rotated by 30 degrees, some by like say 90 degrees, some by, I don't know, like 300 degrees or something. But crucially, like you do actually get to see every class in every sort of rotation. So it's not that we only rotate 1s by 30 degrees and we only rotate by 2s by 90 degrees. There is actually sort of a relatively even allocation of digits across the different rotations. But if you evaluate a model trained on this data using more data that has the same rotations that were in the training data set, then you get the blue line. And if you sort of leave out some of the rotations to be sort of like novel rotations to use as a test set, then you get the red line. And this x-axis is a measure of model capacity. So we train linear SVMs on the raw pixels because we can actually sort of quite accurately control and measure the model capacity of linear SVMs. And we found that, yeah, if you sort of exhaustively look at all of the different model capacities, then yeah, you do actually end up needing, you sort of peak in a different place on the sort of overfitting, underfitting trade-off for these two different types of evaluations where you've got in-domain and out-of-domain. And typically the out-of-domain one does need stronger regularization. So we actually repeated this experiment on a variety of different data sets. I think there was like 6 different data sets, and with the same sort of setup. And every time the out-of-domain evaluation needed much stronger regularization to get higher performance. So the other thing that we were wondering is, at the moment in the domain generalization research community, there's sort of like a big sort of mess where like none of the evaluations are sort of that happening in different papers are consistent with each other. All the like, if you look at one paper, then one method's the best. If you look at another paper, then the ordering of methods, even like the baselines, is like completely different just because of some reason that no one seems to really understand. So we were wondering, is the relative performance of DG methods essentially random and only happening because of some sort of implicit regularization effect that is, caused by, say, different optimizers or a different choice of optimizers or other sort of tangential experimental setup details that one might not expect to actually impact the final conclusions that much. So we trained a huge number of models in like lots of different ways, using lots of different domain generalization methods. And the particular sort of like setup used to train each of these models is not super important. But then we retrospectively measured the complexity of each of these models and the performance on these DG tasks on this particular plots for PACs. And we found that to some extent, the performance of DG methods can be explained by implicit regularization, but it's definitely not like a noise-free picture. But I think this whole sort of question is still like a little bit inconclusive, and it's down to the fact that we can't reliably estimate, reliably explain why neural networks work using Rademacher complexity, well, at least not yet. So I think this is something that I might come back to in a few years once we actually have some better ways of analyzing neural networks with Rademacher complexity. But at the very least, you do seem to get this sort of like, on the left-hand side, this obvious underfitting region. Then you get a small peak as you increase the complexity. Then you get a very, very mild overfitting region. The intuition that most people have is that, as complexity gets higher and higher, you should overfit more and more. But for some reason, that doesn't seem to happen that much. And if you actually look at sort of, complexity accuracy trade-off plots and sort of standard i.i.d. learning settings, then they actually end up being quite a similar shape to this as well. So the other thing, which is I found a little bit surprising, I talking to people, this is sort of a contentious issue actually. To me, it seemed kind of obvious that if you want to tune a model to perform well on domains it hasn't seen yet, you should do some sort of like leave one domain out cross-validation style thing, rather than just ignoring the sort of domain annotations in your data set and just doing conventional cross-validation by randomly allocating instances to different folds. But it turns out, no, yeah, doing this sort of leave one domain out cross-validation thing gives you a much more reliable signal for tuning hyperparameters. I didn't include a table here just because it's sort of messy and not that interesting to look at. But I think I'll send round sort of a copy of the slides and maybe a couple of links to papers where we've done this stuff after the talk that maybe Alex can help distribute. So moving on to meta-learning now. So I'll talk a bit about generalizing these Rademacher complexity bounds to the meta-learning setting as well. So just to introduce people to meta-learning a bit, since it might be a new thing for some of you, or for a lot of you. The idea is that you start with some meta-learner. You feed it a collection of meta-training tasks, or training tasks. And then after it sort of had a good look at some of those training tasks, so, one of them might be some omniglot or MNIST style classification thing. One might be, classifying different birds. Another task might be something that looks a bit like ImageNet or texture analysis. After you give the meta-learner those training tasks, it gives you a learner, which is sort of specialized in a sense that if you give this learner a new training data set that is in some way, related to the data set seen during the meta-learning process, this learner should work better in some way. I'll get onto, what in some way means in the next slide. So for example, if you give this learner MNIST, then it should be able to produce for you a classifier, which, when given a digit, a photo or an image of a digit, can actually tell you what digit is in there. So why would you do things this way? This seems needlessly complicated compared to just having, the learners that we already have. Like PyTorch already exists. It already has SUD implemented. We've already got, Torch Vision, which has all of these architectures pre-implemented for us. Why do we need to bother with this whole meta-learning step? So I'll give you the theoretical explanation about why it can be useful. Sorry about that. My Firefox crashed.
No, it's okay.
Okay.
That's all right. I thought it was just me.
Yeah, same. Yeah, we should probably try turning off the cameras.
Yeah, I don't think it was like any issue with bandwidth or anything. It's just Firefox actually like an exception and said, sorry, I need to close now. Not really sure why. So I think it was
Yeah.
Okay, so I think I just finished this slide.
Yep.
Okay, cool. So yeah, so I'll explain a little bit about why, from like a theoretical point of view, this could be useful, and then how you can derive sort of what I think are at least interesting theoretical bounds for this, and then how you can conceptually at least action those bounds to create an algorithm that actually works a bit better. So, I've changed notation a little bit here, but it'll become a little bit obvious soon why I've done that. So, and it can, like, for a model, you might, yeah, so the typical way that we can represent a neural network is that it is some function f that is parameterized by some weight vector from some set of weight vectors. And this takes in an image as input and produces for you some sort of estimate of some idealized ground truth value. So this estimate is y hat, the ground truth value would be y, I guess. And this set of permissible weights can be quite big. So it could just be like, sort of, everything reachable from the origin within, like, 10,000 steps of gradient descent. That's a very vague way of defining it, but you could have a more strict definition if you've got some sort of fancy regularizer that constrains the norms of weights, like some of my previous work has done. And then we know, just sort of, this is a little bit of a caricature of what we talked about earlier, that roughly speaking, the size of this set of weights is, and the square root of the amount of training data that we have is proportional to how badly our model could overfit. So that's sort of roughly what Rademacher complexity is saying, and this is a little bit of a caricature of that bound. So in a meta-learning setting, we again define some sort of higher level probability distribution in this calligraphic P over different tasks, and then we can sample different tasks from this distribution over tasks. So for example, P1 could be this sort of omniglot data set thing. We've got some random alphabet that I don't know what alphabet that is, but we've got some instances from this alphabet that we want to classify. And then, P2 could be something to do with birds, and then P3 is this other sort of, texture or ImageNet style thing. And then what our meta learner, what should be the goal of the meta learner, this is what I'm going to try and convince you, is that we should find some theta prime, so capital theta prime, which is a smaller subset of our original weight space, and we should try and constrain the solution or the models for all of these tasks to lie within this subset. So we end up getting a much smaller theta prime. So yeah, the idea is that we want the size of theta prime to be much smaller than theta, our original sort of weight space. And as a result, that will make this sort of caricature bound I've got in the top right corner tighter. So therefore, if we have, on some novel task, we have a similar number of instances to some tasks that we're training a model in our original weight space with, then we should expect maybe better accuracy using our meta learner. Or if we have fewer training instances than some sort of conventional learning algorithm is presented with, then maybe we should expect the accuracy to actually not degrade even though we've got less training data. So the whole idea is that meta learning allows this learned learner to be more sample efficient, so it can get better accuracy with less data. So it's a little bit painful to talk about meta learning theory, because you just end up having to sort of keep a lot of different quantities in your head at the same time, because all of the sort of sources of error sort of decompose into more sources of error, and you just go like track where everything's going. So I've tried to keep the number of things that you guys need to sort of keep in your head to a minimum. Hopefully that works out. So we have we can define these two quantities here. So the meta training error. So this is analogous to your training error, and this is just going to be the mean training error on each of your training tasks. So we had 3 training tasks in the previous slide, one on that sort of black and white alphabet thing, one on birds, and one on either ImageNet or textures. I can't quite tell because they're too small. And then we have this meta test error. So this meta test error is the test error on tasks that we haven't seen yet, which is not the most intuitive thing to think about. So it's not the test error on those 3 tasks on the previous slide. The meta test error, for example, could be the test error on MNIST, like we had in that first slide on meta learning, how we deployed our learned learner on MNIST. Except it's also the expected test error. So it's the test error averaged over all of the tasks that we haven't seen. So we can then define this, what I'll call the meta gap. More precisely, it should be called the meta generalization gap, but that's a bit of a mouthful, so I'll just call it the meta gap in this talk. So again, similar or analogously to the standard i.i.d. learning setting, this is just the difference between our meta test error and our meta train error. I've expanded the definitions here though, just to keep things ticking along. And this is where I'm hoping I don't lose too many people. So we can now, using tools that we already have, you can already say that the meta generalization gap is bounded by this. So what you can do is that you can expand the test error inside this expectation and just replace that with the upper bound that we already have from the i.i.d. learning setting. So what you end up getting is that for these novel tasks, the test error is bounded by the chaining error plus 2 times the Rademacher complexity of a hypothesis class that we've learned. So then I've rearranged things slightly a bit. So the Rademacher complexity and the training error have sort of swapped places, but addition's commutative, so that's fine. So what we end up getting is that we now actually just need to bound this quantity here. So what is this quantity? So the right-hand term is just obviously our training error on the tasks that we do get to see. So that hasn't changed. That's hopefully a little bit intuitive. The thing inside the expectation, that's the training error on the tasks that we haven't seen yet. So in a sense, these 2 terms on the right that we need to deal with next, they are a measure of how reliable is our estimate of the training error, which seems like a little bit of a weird thing to sort of get your head around, because training error shouldn't really be an estimate of anything. But in the meta-learning context, you do actually need it to be an estimate of something. So this is where we get into the sort of idea of meta-overfitting, which is something that is still counterintuitive for me sometimes. So bear with me. So this is going back to our sort of diagram from a couple of slides ago. We had this idea. That our meta learner wants to find some small subset of our weight space and say, constrain all of our solutions to line here. But obviously, the meta learner is choosing which subset of our weight space to actually select as our hypothesis class based on the particular training tasks it's been given. And it's only been given a finite number of training tasks, just like how in, so that means that it's liable to overfit, just like how in the standard i.i.d. learning setting, because training sets are a finite number of examples, it's not like entirely representative of the underlying data distribution. It's an approximation. So it could be that if we gave the meta learner a different set of tasks, it might give us a hypothesis class here, or maybe one here, or maybe one here. So what we actually care about is how sort of stable is our meta learner with respect to this subset of weights that it will give us based on the training tasks that we give it. So to do this, we need to define a hypothesis class family. So this is now going to be a set of hypothesis classes, which is painful to think about. So one of the issues with meta-learning from a theory point of view, and when I think there's not been that much work done in it, is because it's really quite painful to think about, because you get all of these hierarchies popping up everywhere, and there's just sort of like so many things to keep track of. But to try and give you some intuition about what F might be, or this sort of blackboard F might be, it could be, you can think of this hypothesis class family as the set of all places that you could put the subset. So the set of all centroids where you could put the subset. So it could be centroids in weight space, or it could just be a shared feature extractor. So it could just be that you've decided that your meta learner is going to learn the feature extractor, and then your downstream learner is just going to use this pre-trained feature extractor and only learn the final classification layer. So that's sort of like a relatively contrived toy example of meta learning, but still sort of fits into the meta learning framework. Or you can do something a little bit more fancy and actually select several different regions defined by several different centroids and use like the sort of the union of these different regions as your hypothesis class, but that ends up being quite painful to work with in practice. So I don't think that's an idea that's used very much. And there's probably many more ways of actually defining this hypothesis class family, but again, it's a little bit painful to think about. So people tend to just stick to the basic ones of either using a shared feature extractor or using some sort of centroid in weight space. So to tie it back to some, for those who are familiar with sort of few-shot learning and meta-learning, examples of methods that use the shared feature extractor approach are things like prototypical networks, and something that uses the centroid and weight space approach is MAML. So MAML sort of has this weird episodic sort of gradient-based meta-learning thing where it finds a centroid, and then it implicitly enforces like this smaller subset by only taking a couple of gradient descent steps, so you can't move too far away from this pre-trained centroid that is found during the meta-training process. So I'm not going to go through the derivation too much because it's actually getting a little bit repetitive. It's pretty much the same idea as the domain generalization case, where you sort of write out the training error for the different training tasks that you have, and then you sort of construct this repeated holdout thing where you have some tasks are sort of meta test tasks and some tasks are meta train tasks, and then you use these sort of sigma random variables to assign each task to a meta train and each task to meta test. The one different detail is that now this supremum is over your hypothesis classes as opposed to just individual models. So there's like this meta level happening. So it means that constructing upper bounds in this Rademacher complexity for a particular choice of hypothesis class family becomes a bit more difficult in practice. So I'm not going to talk about how you can actually go about and do that, because that ends up being sort of just pages and pages of equations with very little in the way of intuitive explanation. But the sort of moral of the story is that you end up bounding the meta-generalization gap by, again, 2 Rademacher complexity terms. So one for sort of each layer in this data generation process hierarchy, where one of them is looking at how much each individual task can overfit, and then the second term is looking at how badly your meta learner could have overfit the particular set of training tasks. So something that I think is sort of important to point out is that because we've been able to find a much smaller focused set of theta prime, or in this case f, for our particular tasks that we care about, this first Rademacher complexity term ends up being much smaller than a typical supervised learning Rademacher complexity. Because usually, if you think about it, like if you're in some standard supervised learning setting and you're not using any sort of like pre-trained models or anything like that, then if you're going to train a model on, say, MNIST, then you're just randomly initializing your weights, and you don't really have a good idea about what direction those weights are going to move in. So you need to just have relatively few constraints on how those weights can move during the training process. In the meta-learning case, the whole idea is that you use your collection of meta-training tasks to actually find like a pretty good idea about whereabouts in weight space you should initialize. For example, if you're using one of those centroid-based hypothesis class families. So typically, this first Rademacher complexity term ends up being much smaller than the comparable quantity in standard i.i.d. learning. So an example of meta learning, which is maybe it doesn't. So we didn't actually use Rademacher complexity to do this. This is actually, I thought I'd include this not so much as an example of how Rademacher complexity can be useful for meta learning, because we have yet to figure that out, to be honest. It's sort of a work in progress. This is some quite recent work that we've done sort of earlier this year. But this meta QDA is something that me and colleagues did about 18 months ago or so. And it's using a more sort of Bayesian approach, which I thought I'd include here, just to broaden people's minds a little bit about the other possibilities within learning theory for doing meta learning. So for those who are not super familiar with QDA, it might have been quite some time, or maybe it's not that popular in the syllabus anymore. Here's my one-line summary of QDA. So it's quadratic discriminant analysis. What it does is that it fits a Gaussian to the training data within each class in your training data set using maximum likelihood. And then when it comes time to predict the class of some novel test instance, you just predict the class that gets the highest likelihood evaluation for each one of these Gaussians. So you evaluate the likelihood of your test instance for each one of these Gaussians and then predict the class that corresponds to the Gaussian that got the highest likelihood. So what I did as like sort of a toy example for this project was generate some sort of like 6 different training data sets using the same data generator. So like all 6 of these data sets, they're just sort of different realizations of the same underlying data distribution. It turns out QDA, and this is something that's sort of relatively well acknowledged, QDA does not work very well with small data sets. You need typically quite large data sets in order to estimate all of the covariance matrices and things accurately. So if you should expect that, if you have a reliably fit model, then all of these decision boundaries should be roughly the same. Since they're not, that's a sign that this particular algorithm is liable to overfit. So there's more formal arguments from the sort of algorithmic stability community that can back me up there, but I won't get into that. But one alternative way to thinking about meta-learning is that it is a way to construct very informative priors using related tasks. So you do have to be a little bit careful about how you're sort of encoding this knowledge that you're gaining from prior tasks, so that's actually encoded in a reusable way. But for this particular project, we used like all sorts of like nice conjugate prior sort of things to make it all the solutions sort of closed form. So we ended up having like a normal inverse Wishart prior on our Gaussians, and then we sort of learned the parameters of those normal inverse Wisharts using like a meta-learning setup. And then when it comes time to actually deploy to some novel task, we can fit the Gaussians using mapped inference instead of maximum likelihood. So we actually are able to use this prior that we've meta-learned on relevant tasks to stabilize the entire learning process. And we end up getting much more stable decision boundaries, which then leads to less overfitting. So there's a whole other sort of corner of learning theory that is growing in popularity, which I'm still not hugely familiar with, but I'm sort of becoming motivated to become more familiar with it. It's called Pac-Bayesian Analysis, and that's this idea of analyzing Bayesian classifiers using statistical learning theory. And it typically gives you the tightest bounds, so you can actually get actually useful bounds for neural networks with Pac-Bayesian analysis, but you are restricted to using Bayesian neural networks. So that might be a deal breaker sometimes, but if that's not a deal breaker and you need to have, for whatever reason you care about having tight bounds, then Pac-Bayesian analysis is for you. So I'll sort of wrap up a bit with a bit of an outlook on where I see things going, or what the sort of underlying benefits are to what I've done this. So I think hopefully, I don't know how well I might have convinced you that this is true, but hopefully Rademacher complexity, hopefully you can see that Rademacher complexity is something that can be adapted relatively easily to new settings. So I've adapted it from this i.i.d setting to domain generalization meta-learning. And it's relatively intuitive if you can set things up in this sort of generalization gap formalization. Something that I've alluded to, and since I'm pretty much on the deadline now, I'll not go into much detail, but I think something that we'll see more of in the future is a bit more, something that is needed, and I think we'll see more of in the future, is more investigation into how you can analyze neural networks with Rademacher complexity. But just to convince you that what I've done is still useful, you can actually use Rademacher complexity for these like sort of shallow linear models and still use that in conjunction with pre-trained neural networks, because the pre-trained frozen backbones don't actually contribute to the Rademacher complexity. So if you're using sort of like, these self-supervised learned backbones and some sort of domain generalization setting where you're actually just training the final linear classifier, you can still use these Rademacher bounds for whatever reason you might want to use them, say structural risk minimization for model selection. And finally, I think this is a much more general sort of point, is that I think future research in domain generalization, which has really stagnated in performance recently because people have realized that everything they're doing is sort of like not effective at all, and that all of these conclusions they're making are actually just sort of random noise in the experimental setup process. And also meta learning, where we're beginning to start sort of see the same sort of problems. I think in order for these problems to actually start progressing, or the solutions to these problems to actually start progressing, the methods need to take into account more meta information about domains and tasks. So for example, in that MRI case, maybe the learning algorithm should have some facility to be given information about the population demographics or the particular type of machine or its calibration parameters that are being used. So I think I'll leave that point there for now. So I don't know how strict this deadline is for things like questions. I'm happy to take questions if people are happy to stick around. If everyone has to go now, then so be it. You can email me if you want.
Yeah, thanks very much, Henry. Yeah, we'll have plenty of people still here. So if anyone has any questions, feel free to ask.
I had one question just around the use of the supremum in the definition of the Rademacher complexity, and whether it might also be useful to look at things like an approximation of the Rademacher complexity or a lower bound, where we're also able to bound the kind of the distance between our approximation and the true complexity. So say instead of taking the supremum, we took the expected value, and I don't know whether it's possible to place some sort of tail bound around the distribution of the expected values, but whether that would be something that's useful, especially in those cases where, for the more complex cases where we can't necessarily compute that supremum.
Possibly. So if you just drop the supremum completely, for example, and just have an expectation in there. So I suppose it really depends on what the expectation is over. If it's over the data, then strictly speaking, Rademacher complexity already has an expectation over the data as well, and empirical Rademacher complexity is what I've actually been talking about here. If you drop the supremum completely, then that the current definition of Rademacher complexity will actually always evaluate to 0, because those Rademacher random variables will there'll always be like another term in that expanded expectation over them that will cancel out things. If you want to instead have some sort of expectation over models, for example, instead of a supremum, then you require a distribution over models, which is perfectly fine, but you now need to have some sort of like Bayesian classifier, and that's actually what Pac-Bayes deals with. So that's moving away from Rademacher complexity, but you then arrive at something like Pac-Bayes. So if you're interested in that sort of thing, then definitely check that out.
Gotcha. Yeah, that makes sense. I guess I'm just considering that, like, while we're assuming that we're always taking the worst case scenario, in reality, we might never hit upon that worst case scenario, or we might always be in the 20% better.
Yeah, exactly. So this is this idea of that whole idea is called uniform convergence, where the idea is that this bound is true for every possible model in our hypothesis class. And recently, like I think at ICML last year or something, there was some, I don't know if it won like best paper, or it was at least like shortlisted or something. It was saying, oh, maybe we need to move beyond uniform convergence. And there's been a lot of like arguments, as theoreticians tend to do, about whether that's actually correct or not. But yeah, I think you're sort of on the right track. That people are starting to think about, is there something we can use other than the supremum?
Gotcha. Yeah, thanks for the talk. It was fascinating.
No worries.
And Henry, I have a very general question. But I'm not too familiar with meta learning. So, what's the relationship between domain generalization and meta learning? Do you consider meta learning as a tool to solve, like, to help improve domain generalization?
So I think in terms of problem setting, they're probably different. You kind of see every now and again I see a paper that sort of tries to shoehorn meta learning into being a solution to domain generalization, but I've not seen anything convincing in that sort of space. But I think conceptually they're related because if you think about this standard i.i.d learning setting, then you've got like a single layered data generating process where you have some distribution and then all of your instances are sampled from that distribution. So I think what domain generalization and meta learning have in common is that they both move to a hierarchical data generating process. So for both of them, you have some higher level distribution, and domain generalization is a distribution of domains, and meta learning is a distribution of tasks. And then after you've sampled several domains or several tasks, you then sample data from each of those domains or tasks. So this sort of, it's domain generalization and meta learning for me is two interesting ways in which you can introduce hierarchies into the data generating process. And in general, what I've become sort of interested in recently in the last couple of years is how you can be more aware of your data generating process and any hierarchies or other structures that exist in it to better design learning pipelines, either for an individual task or a collection of tasks.
So are you saying the difference between domain generalization and meta learning is that in domain generalization you're considering different domains, and then in meta learning you're considering different tasks?
Yeah. So to make the difference more clear as opposed to the similarities, the difference would be that in domain generalization, all of the domains have the same classes.
Okay.
So you have one model that you're deploying to all of the domains. In meta learning, each task has a different set of classes, and you actually train a different model for each one of these tasks. But there is some sort of like restricted hypothesis class that you use to actually constrain that those models aren't too dissimilar from each other.
Yeah. Thank you. Yeah, any other questions from the audience? There's a question in the chat.
All right. So why do I prefer Rademacher complexity? Okay. So broadly speaking, there are 4 different tools that people generally use for analyzing the sort of overfitting behavior of learning algorithms. The classic one that I think is still sort of rooted in people's minds as learning theory is VC dimension. So that's the one that was sort of like, was responsible for spurring the development of like support vector machines. So VC dimensions, bounds based on VC dimensions tend to be quite loose, and they also can't take into account what we call the margin of a prediction, which is, it turns out, it tends to be quite important for actually making bounds much tighter. So Rademacher complexity does take into account the margin of predictions. So you can use things like hinge loss and normalizing by the margin to actually make bounds tighter. So that's like quite a technical point that is maybe not super intuitive based on the talk I've given today. So yeah, classic method is VC dimension, but that's sort of old and loose compared to Rademacher complexity. Another one is algorithmic stability. So that's where instead of analyzing a hypothesis class, you actually analyze the learning algorithm. That works quite well for basic algorithms, or when you have like strong convexity for your training objective, but it's any analysis of things like neural networks has just completely fallen over with algorithmic stability. And even like, I think some like decision tree algorithms can't really be evaluated with algorithmic stability. There's various things where it just sort of falls down and is not really that applicable. So it's just generally not as applicable as Rademacher complexity. So that's why I prefer Rademacher complexity over algorithmic stability. And then there's Pac-Bayes, which is the fourth one. I am warming up to Pac-Bayes, but as I said, it's restricted to the case where you have a Bayesian classifier. And in practice, most of the time, we don't actually have a Bayesian classifier. So if you want to use a Pac-Bayes bound, then you have to have a Bayesian neural network, for example. So if that means you actually have to sample weights from some posterior over weights, and then actually pump your instance through 100 different neural networks with different weight samples, and then average the output. And then a Pac-Bayes bound will apply to that particular network, or that particular sort of method of generating neural network ensemble type things. So I find that Rademacher complexity is more general in the sense that it can be applied to things that are not Bayesian classifiers. And I think it's also possible to apply Rademacher complexity to Bayesian models as well, but you don't really see that very much. So so I'd say that it's so why don't we have a Bayesian classifier usually? So I mean, sometimes we can. It's really that's really one of those things where it's a design choice. So for example, a linear model is in general not a Bayesian classifier. If you train a logistic regression model, like there's sort of core idea of a Bayesian classifier is that you have some sort of prior over your model parameters and then a posterior over model parameters. So you don't just produce one weight vector at the end of your training process, you produce a distribution over weight vectors. And then the way that you actually make a prediction is that you average the predictions over all the different samples from that distribution. So it ends up being sometimes a bit of a messy process to actually implement in practice.
So in machine learning, we very often have to consider about the efficiency of the algorithms, like the scale of the algorithms. But most of the Bayesian methods are quite expensive.
Yeah, that's definitely improving, which is I'd say one of the reasons why I'm warming up to Pac-Bayes as a tool for deriving new algorithms rather than trying to explain existing algorithms.
Cool. Any other questions? Probably have, if anyone have other questions, we'll have maybe 5 more minutes. Yeah. If there's no question, then we'll wrap it up.
I've got a quick question just about continual learning. So I've read a bunch of papers, a few papers on continual meta learning, and it seems like a similar idea, but that the tasks might not necessarily be i.i.d. So you're learning incrementally, right? So you might have one task, data coming in from one task for say 100 observations, and then it switches to a different task. So would that affect the bounds?
So I'll preface this by saying I'm not that familiar with continual learning. I've got a few colleagues and friends in Edinburgh that do it, and I've talked to them a bit about it. So I may have the wrong impression about how it actually works. But my impression is that the main thing that they tend to be worried about is this idea of catastrophic forgetting. So that when you switch to a new task and you start updating your model on this new task, you want to make sure that you don't forget how to do the old task if it comes around again. So I think that's the main goal of continual learning. But it's always sounded to me like continual learning is more of like an online learning problem. So it's, as you said, it's incremental. There's actually like a whole other branch of theory that in some ways it sees itself as distinct from statistical learning theory, and it's dealing with online learning problems. And typically, Rademacher complexity is not used for analyzing online learning problems. There's actually, you get like these regret-bound sort of analyses that are very algorithm specific, and it ends up being a little bit more like the algorithmic stability stuff that I talked about, but still distinct from that. And so yeah, generally you don't actually get Rademacher complexity analysis of things like continual learning. But again, I'm not sure if anyone's actually tried to do it specifically for continual learning. It's not obvious to me, at least, maybe because I don't have the right background to figure out how to do it.
Right. Cool. Yeah. Thank you.
Any last questions? Okay, I think that's it. Let's thank our presenter. Yeah, thank you very much, Henry. Hopefully I can see you again sometime in person.
Yes.